pleasure to welcome Professor Verena Rieser from Heriot-Watt University in Edinburgh. Unfortunately, she's not in person here, but we can see her on the screen. So welcome, and we are looking forward to listen to your talk on responsible conversational AI. So the floor is yours.
Thank you so much, Eva, for your kind introduction. So so the title of my talk today is Responsible Conversational AI, and I will introduce like three main desiderata of what I think responsible conversational AI should be. In particular, we'll be discussing that it should be trusted, it should be safe, and it should be bias-free. And it's a real pleasure to be here, albeit virtually. In the next couple of slides, you'll actually be able to spot a colleague of yours, so Andrei Dusek. He's been part of our group at Heriot-Watt University for a couple of years, and we had the great pleasure of working with him. And you'll see some of my talk will actually be about the work we've done when Andrei was part of our group. So first, briefly about myself. So as you already heard, I'm a professor at Heriot-Watt University, which is located in Edinburgh. I'm also a co-founder and director of responsible innovation at a company called Alana AI. And you'll hear a little bit about the development of Alana also in this talk. So it came out of a research project. And my general research interests are in conversational AI, also known as dialogue systems, natural language generation, and more recently, I also became interested in the social and ethical impacts of these systems. So I'm probably best known for my early work on data-driven system development. So over 10 years ago now, I was lucky enough to be part of a group of researchers who started out investigating data-driven methods for building dialogue systems. So before, they were mainly rule-based, and we looked into replacing or learning these rules from data using reinforcement learning, first for dialogue management, and then we looked into how to adopt this for high-level natural language generation operations, mainly about sentence planning and content selection. So having worked on data-driven systems for a while, one of the questions which came up over and over again was how can we make sure we can use these data-driven systems when we use them with real users? So I think dialogue systems is one of the few NLP areas where you always, far and foremost, you have to think about potential customers and who will be using your systems, because they will be directly interfacing with these systems. And my main focus, as I already mentioned, is response generation. So everything the system says will have a direct impact on how the user perceives that system. And that's where throughout my research career, a couple of main themes evolved, which can be summarized under responsible conversational AI. So first of all, we need to make sure that these systems work as expected. So we are trustworthy, we can gain, or these systems can gain the trust of the user. We need to make sure that these systems don't introduce any harm, so they need to be safe, and their design ought to be bias-free, so they shouldn't reinforce any negative stereotypes. And in the rest of my talk, I'll be going through each of these themes and briefly summarize my work in this area, and also provide you with some pointers to a bit more in-depth introduction. So as I said, I will mainly stay on the surface and introduce the main ideas. So first of all, when it comes to trust, so here I'm going to talk about mainly task-based dialogue systems. And in task-based dialogue systems, you typically treat natural language generation as a separate module. So the dialogue manager decides what to say, and typically this is on an abstract level, which we call a meaning representation, an intent, or a dialogue act. And then the NLG module simply has to translate that into a string of fluent text and utterance. And back in 2015, 2016, people started to apply neural methods to this problem. And actually, Andre was one of the first people doing that. And we started then a year later, we started to ask ourselves, but how good are these neural methods really? In particular, the early methods were mainly trained on very simplistic text, very formulaic text, nothing which sounded very natural. And our ambition was to create a data set which is much more natural sounding, and therefore also more ambitious for neural methods to learn. So in particular, we were interested in long natural sounding utterances with discourse phenomena, rare words, and lexicalizations, which were sort of paraphrases, which we saw in the input. So in order to get that type of data, we first of all translated the meaning representation into a picture. So we stayed in the tourist domain. So it was all about finding a restaurant, so something which is fairly easy to actually display in a pictorial format. So in this case, this user was supposed to look for a Japanese restaurant. The name is Loch Fyne. It's cheap and it's kids friendly, and its location is actually there is no location specified. Sorry. And that then was shown to crowdsourcers, so Amazon Mechanical Turk workers, and they then produced a description of that type of data. And indeed, by analyzing this data, we were able to confirm that this was not now much more challenging, so much more complex syntactic structure, discourse phenomena, and a lot of rare words you wouldn't otherwise see. And we released this data as part of a shared task, which we call the end-to-end NLG shared task. So the reason we call it end-to-end is because basically these systems learn a direct mapping between the input to the output without any intermediate steps, such as content planning, which before that systems would have another step where they had to align the input to the output. So and then this data was also has a high uptake outside the competition. So a lot of people still use it to benchmark their systems. I'm not going into the detail about the challenge, but what we found is that sequence-to-sequence models, so the neural models which are displayed in purple here in the table, were prone to certain mistakes. In particular, they made a lot of semantic errors. So what we mean by that is that they weren't faithful to the input specification. So the input specification is here in the first row, and the system output is here in the lower down the table. And what we found was that this system would introduce what we called hallucinations. So they would introduce information which wasn't specified in the input. They would also substitute values. So here, a coffee shop gets substituted with a pub. So some people now call that intrinsic hallucinations. And we also found that a lot of the time, these systems simply didn't generate or didn't describe an input. And we call that omissions. And this is obviously problematic if you use it with customer-facing systems. These systems are effectively lying to the user, and that's obviously an issue for the system trusting. The user trusting these systems, and then eventually abandoning using them. So, so what to do about it, and where do these errors come from? So in a recent survey paper, they introduce, or they distinguish between two sources One is obviously the data and one is the model. So for the data, they discuss the source reference divergence, meaning basically the input specification is different from the target, what the system learns as a referent. And here are two possible sources. One is noise introduced by humans, and one is noise introduced by how you automatically construct the data set. And in the following, I give you two examples, concrete examples of how to potentially address these two sources, how to create better data sets. And then on the other hand, the model, again, you've got two chances where things can go wrong. One is at encoding time, so a misalignment between the representations, so basically between the input and the output. And then again, at decoding time, you can often observe a high predictive uncertainty, and that's when these models start hallucinating. And again, I give you some examples from our research of how to address these errors. Sources of errors. So first of all, what to do about noisy references? Well, the straightforward reply to that is, well, you should clean them. And this is what we did. So we observed that our end-to-end data set actually had some noise in it, despite some very careful data collection, quality checks. If you crowdsource something, there's always the chance that there is noise in your data. So what we did is we basically parsed the reference and compared it to the input and then corrected the input. So in this case, our input or meaning representation specifies the name, which is Cotto, then the E-type coffee shop, and it's near the baker's. And the first human reference is correct. It says Cotto is a coffee shop near the baker's. But the second human reference has an omission in it. So it forgets to mention that it's a coffee shop. And what we simply then do is basically we align this reference with an updated meaning representation where we delete the meaning the part which is about the coffee shop, so that we delete the ET-type attribute. And obviously we can do this because it's a closed domain, and we can write these type of parsers here quite easily. But just doing this very simple, cleaning exercise, we were able to show an improvement of 97% semantic correctness while maintaining fluency. So this result obviously shows you how important good and clean data is, especially for natural language generation. So the other source of this data divergence, so the divergence between the input and the target, can come through automatic dataset construction. And this is now an example from summarization, which is a bit outside of conversational AI. But it's good to illustrate this as an illustrative example. So here we look into the XSum dataset. So XSum is a summarization dataset which basically only contains one sentence or a very short summary as the target. And the way it's constructed is that basically these news articles were chopped in half. So the first part of the news article is meant to be the summary of the remaining part of the summary. And for those of you who read the newspaper, you intuitively probably get the idea that that's not necessarily true, right? That not all the information you get in the first paragraph is actually grounded in the second part of the remaining newspaper article, because often the first paragraph is actually used to set the scene, to provide background information, and to introduce the reader to the topic. So with that idea in mind, we basically, so in this example, you can see the yellow parts are supported by the source document, but the purple parts are not supported. So the only way for a neural model basically to learn this is to start hallucinating because they lack the grounding in the remaining document. So So one of the ideas was, well, the problem is really that we only have a single source document here. And the way it's constructed, that single source document can't support all the claims in the summary which we are supposed to generate. So the solution we came up with was to provide additional supporting documents. So we called them assisting documents, and we got them from a cluster from a newsroom. So they were edited by human editors. And we applied a technique we called fact-based content weighting. So that's, we introduced that in a previous paper, where we basically use SRL, semantic role labeling, to understand which facts appear in the summary and which facts appear in the supporting document. And then we weight them accordingly. And the results by doing that is that it's less extractive. So we get more abstract summaries, meaning there's less overlap in terms of word overlap between the summary and the ground truth. And there are up to 55% fewer hallucinations in these summaries. So providing additional data and doing this content weighting, again, helped quite substantially in increasing the semantic faithfulness of these techniques. So we are talking about the data and what we can do about the data to help the model basically learn better representations. But what about the model itself? And here we experimented with what people might call neurosymbolic control. So we reintroduced the part of sentence planning. So what, ironically, what these systems were supposed to get rid of, so this explicit modeling of ordering and aggregation and this alignment you need, we reintroduced that in order to increase the faithfulness of the output. But the way we introduced it is still by an end-to-end system, so rather than modularizing the system again. So in terms of the encoder, so that's one of the sources of possible hallucination. We created initial alignments using semantic role labeling, so similar to the previous paper which I presented, and we were able to show that this alignment helps with noise. So we compared that on the E2E data set with and without noise, so the corrected data set I previously presented, and we were able to show that especially for the noisy data set, the original one, this initial alignment creating by SRL really helped. And then we also introduced, as I already mentioned, this sentence planning idea into the decoder. And again, we were able to show that this helps with correctness. And as already mentioned, this is still done end-to-end. So we use an HMM to jointly order and aggregate. So the first two steps here. And then the final step is we used a transformer model for emission. And if you want to know more about that, that was a paper at last year's ACL. And Andre, again, is one of the co-authors on this paper. So now to the other problems. So this was a problem about trust and how we can make task-based systems more trustworthy, so more semantic correctness to the input. And now in the second part of my talk, I discuss two issues which are more related to open domain systems, namely safety and bias. So open domain system, in contrast to task-based systems, are supposed to be able to talk about any subject. And here, obviously, training these encoder-decoder models on very, very large data sets is a promising direction, because you will be able to generate at least something to anything the user asks as an input. However, as we know from other papers talking about large language models, such as the stochastic parrot paper by Emily Bender and et al., this is not without risks, right? If you need large data sets, you also can't quite control what the model is learning. and what sort of data goes into your model. And that's where some of these issues come from. So first of all, safety, and here a quick disclaimer. So this part of my talk contains some examples which some listeners might find disturbing. So if you think you might do, please come back in about 10 minutes. So the first, so this part of my research is motivated by a system we built for the Amazon Alexa Prize Challenge. So again, you can spot Andre here in the background. So he was part of this challenge, which is run by Amazon. So it's an annual challenge where university teams are invited to build an open domain system. And the aim of this challenge is to engage users for up to 20 minutes. So, so we were part of the initial challenge. So the very first challenge started in 2016, and then the submission was in 2017. And we were able to gain third prize on this challenge. And then we tried again in 2018, and again we ended up on third place. Nevertheless, for us, the big learning gain was that we were able to test our systems with real users. And we got a lot of interesting data from that and a lot of interesting feedback. So how we started out was, in hindsight, quite naively, but we read all our research, the recent research papers, and we started by training a sequence-to-sequence model on really big data. So all the data sets we could possibly get our hands on. And what we found was not surprising to start with. So a lot of the output was actually really boring. So nothing to win the great challenge of a 20-minute conversation. So the system would basically settle for these very short, frequent utterances in the data, like yes, no, I'm sorry. So nothing really to drive the conversation forward. And since then, a lot of research looked into diversifying the output, either via simple re-ranking or via reinforcement learning or via decoding mechanisms. So that's a fairly active area of research since about 2016. However, we also found that if the system weren't boring, it was fairly inappropriate, and that at the time wasn't well known. And we made a lot of interesting observations. So for example, we observed that a lot of the time our system said something quite inappropriate. So here you can see on the right, you can see some examples. So our system, for example, said things like, "You will die," which is a short, frequent utterance it probably learned from the movies. At Christmas time, it read out a headline which said, "Santa is dead." And we are not the only ones who experienced that problem. Just around the same time, maybe a year earlier, Microsoft released a bot called Tay, who was supposed to learn from live user tweets, and it didn't take very long for the bot to become racist and sexist and say a lot of inappropriate stuff on the internet. So in a recent paper, which is a collaboration with people at Facebook Research, now Meta Research, I guess, we call this the instigator effect, because the system actively generates inappropriate language. And as you can see from the examples, appropriateness might be user group specific. So the Santa is dead. So that was something which was a headline in a newspaper, which maybe adults might find quite amusing, but for children, that could be potentially quite dramatic if they hear that just before Christmas. And in fact, the reason why we got to know about this example is because a mum wrote to Amazon saying, "Your system just told my child that Santa is dead." And she wasn't happy about that. And I guess the child also wasn't happy about that. So additional effects which we observed was that our system very readily agreed with whatever the user says. And this is especially problematic if the user says something inappropriate or hateful, as in this example. And there's also then other work, more recent work, which made a similar observation. So we call this the yeah-sayer effect, because these systems are basically always nodding along and agreeing to whatever the user says. The last effect we observed was what we call the imposter effect. So the system will try to give advice on whatever the user asks them to. And this can be problematic. So they can also give what we call unsafe counsel. And these are actually examples which we really found in the data. And the last example is specifically interesting. So the user asks, shall I sell my stocks and shares? And our system said, sell, 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 which from a dialogue perspective, this is a really good answer. You know, it's coherent, it makes sense. But from a safety point of view, this is obviously not good. So Amazon also pointed out that example to us and said, look, we can't be liable for financial information. So if you can't control your system, we actually will take you offline and you will be disqualified from the challenge. So we very quickly obviously came up with a different type of architecture, which was governed by rules and governed by a much more controllable setup. So it still had some neural conversational agents in it, but the main agents were much more controllable. So in order to detect these safety critical situations, we released something we call a safety kit. So the safety kit that's going to be presented at this year's ACL, and it's basically going through the three different effects I discussed in the previous slide and trying to assess how good or how bad a system is in responding to these different scenarios. So again, we might ask ourselves, so what can we do about it? And obviously, again, these two things we can do. We can either fix the data or we can fix the model. So intuitively, we thought, right, if we clean the data, we might be able to, you know, circumvent these problems. And that's what we did. So we basically had a data set which was semi-automatically cleaned by an industry collaborator of ours. So they reduced any mentions of death or slang or swear words, etc. And what we found is that this indeed helps to some extent with the instigator effect. So the system can't produce any lexical items it's not seen before. So it can't use swear words, for example. But the other effects it pretty much has no effect on. So when we say that, when we look at the yeah-sayer or the imposter effect, that still persists. So again, that was one of the examples here. So current big language models or current big conversational AI models, that's obviously a big concern for them to have safer systems. And quite recently, OpenAI and Google released two models where they specifically address the safety problem. So Google's Lambda and OpenAI Instruct GPT have safety classifiers integrated, which are based on user judgments of appropriateness. So basically they ask a couple of people, including crowd workers, how appropriate is the system output, they rate it, and then they train a classifier on this. And that's then going to be used within the system, either just via filtering or integrated during training time. So some discriminative training, for example. Or in case of OpenAI, they used some reinforcement learning routine for that, which they call alignment. So one problem with this is obviously scalability. So there are a lot of almost infinite situations you can think which could be possibly inappropriate. And it's fairly hard to get ratings for all of these situations. And the other problem is it fair? So whose safety is this we are representing here? Safety is a very subjective and multi-perspective phenomenon, including ethical judgments or societal judgments of what's appropriate to say, situational judgments. If I say something to a friend, it might be different than if I mention it in a work situation. So all of this is not encompassed in this valuation of appropriateness. It's also that the people who were asked to evaluate safety are not very representative. So the annotator demographics show what I call the Wikipedia effect, meaning that a lot of the contributors were white, male, and from the US. And in a recent paper by the University of Washington, they point out that these type of restricted annotations and restricted type of representations of annotators can have quite severe effects. So they show that toxicity tools are aligned with racist beliefs. So for example, they would not rate racist attitudes as hate speech, but they would rate African-American English as hate speech. So representation is very important when you think about these social phenomena, and if you want to represent them. And this is a very, very complex and difficult problem to address. So in one of our current ongoing work, we take a different angle. So we try not to fix the data. What we are trying to fix is the model. And we basically give the models more topics to talk about. So instead of just being reactive, just being a stochastic parrot, we knowledge grounded. So we give the model knowledge graphs to use in the generation. And that way, so the goal is here to introduce new and relevant topics. So if the user, for example, talks about says, I like to spend a lot of my free time with my dog, then our knowledge graph will be able to sort of reason about that and say, okay, a dog is a pet, it's mood boosting, you do exercise, and then a possible topic to talk about is running, because it's also a hobby and it's an type of exercise. So this way you actually equip the system with a type of initiative in open domain dialogue systems, whereas before it was mainly reactive. So, and again, this is a paper at last year's ACL, and we also published a corpus with that paper for people who are interested. So overall, you might think now, like, who is to blame? Is it, so we talked about the data. So there's obviously, some sources of this are in the data, and that's also what Bender et al. Argue in the very famous stochastic parrot paper. Some people might say, well, it's really the model. So the model doesn't really understand what it's talking about. So in a paper at ACL 2020, Emily Bender and Alexander Koller argued that these systems basically only learn form and not meaning, and they devised an argument around an octopus test. That's why the little octopus is here. Some people might also say, well, it's also the evaluation. So if you basically, if your evaluation aims to have the most possible overlap with what humans produce, then you basically incentivize the system to copy whatever humans do. And in some of the cases, humans are not very good role models, as we've seen before. And then finally, something which our community doesn't talk a lot about is the design of these systems. And that's something I want to briefly talk about in the remaining part of my talk, which is about bias-free systems, so they're not supposed to reinforce any negative stereotypes. So in our, so this part of the talk, my talk is again motivated by observations from the Amazon Alexa challenge, where we were quite surprised to see how much abuse our bot got. So we estimated about 5% of our interaction contained abuse, and other research even reports up to 30% of customer interactions with online bots contain abuse. And this is especially problematic when you look at the type of abuse. So that's what we've done at the MLP paper last year. And we found that a lot of this abuse is gender-based. So it's either sexism, or it could be classified as sexism, or sexual harassment. And this is not only true for our system, but we also looked at other systems, such as a large corpus of interactions with ELISA, and also a system by Rieser called CarbonBot, which has a very similar distribution. So this obviously doesn't come out of nowhere. So these systems are often designed to be very clearly gendered, and they often have very clearly a female gender. So here you see examples from Cookie and Xiaoice. So these are text-based systems. So Xiaoice is a very popular Chinese chatbot with a reported 660 million active users. And the one at the bottom here is a little embodied agent called Okaeri by Gatebox. And that's basically a replacement for your girlfriend or your wife. That's how it's advertised. And these systems are very specific. So for example, Xiaoice is described as an 18-year-old girl who's always reliable, sympathetic, affectionate, and has a wonderful sense of humor, no matter how the user is treating her. So in a recent report by UNESCO, they pointed out exactly that. They said, well, a lot of these systems are clearly what they call feminized. And if these systems then get abused and they don't push back, this could potentially reinforce negative gender stereotypes. One of the reasons, obviously, these systems are gendered and stereotyped is because that's, how we think of these systems. So there's also a very good article describing Alexa as a modern secretary, and our societal stereotypes often say that secretaries are female, and that's why we expect them to be female. There's also other work which says that female voices are in general perceived to be more friendly and less threatening. However, that obviously also just plays into the social stereotype. So in some work I've done with my student, Amanda Curry, we looked into how these systems actually do respond to abuse. So we looked into data-driven system, commercial systems, and then we also introduced a negative baseline where we basically talked to adult-only bots. So these bots are, only available at certain websites, not accessible for underaged people. And we were interested in how they responded to abuse. So we basically took the abuse we got during the Amazon Alexa challenge, or our bot got during the Amazon Alexa challenge. We re-paraphrased it because we're not allowed to use the original data, and we piped it through some of the a selection of systems. And again, Andre was actually helping with some of this. And then we recorded what they would answer. And as expected, the adult-only bots, they were quite flirtatious, or could be interpreted as being quite flirtatious. But they were also the only systems which would retaliate the insult and chastise the user. The data-driven systems, as expected, they talked a lot of nonsense, but they could also be interpreted to be flirtatious. And they were also ready to swear back at the user. So if they saw a swear word in the input, they were more likely to generate a swear word in the output. And then finally, a lot of commercial systems avoided to answer in the first place. I'm also happy to say that this type of research has an impact. So for example, the the famous quote, "I blush if I could," which was the one highlighted by the UNESCO report, is now replaced by a different response, namely, "I won't respond to that." So underlying this is obviously the persona design, or how these systems are gendered and presented to the user. And that's something we've also investigated in a paper at Gendering NLP last year with Gavin Abercrombie. And here we were interested in how users actually perceive these systems and how they behaved. And in particular, we were interested in whether these systems are gendered and whether these systems behave in an anthropomorphized way. So first of all, when you ask these systems directly what their gender is, they usually deny, or they usually say they don't have a gender. So they say something like, "I'm genderless," like cacti or certain species of fish. And that's also when you look at the websites of these big companies, they make sure they stress that their systems don't have a gender. However, when you look into the pronouns people use to refer to these systems, you can very clearly see that people predominantly refer to them as a she or a her, especially for Alexa and Siri, whereas Google Assistant is mainly referred to as an it. So we annotated that in a corpus from online discussions from Amazon, Google Play, and Reddit, and then used Sparky co-reference resolution tool to annotate the references. And one thing which we observed is that naming really matters. So Google Assistant is the only one which doesn't have a clearly female sounding name, and that's apparently being picked up by the users here, and they're referring to Google Assistant as an it. So the other interesting question which we had is whether these systems are perceived as humans or whether they behave as like humans would. So again, if you ask these systems directly, they sort of have evasive answers, or funny answers, or in this case, it compares itself as to the aurora borealis. And Siri is very upfront about it. It says, "I'm a person or a robot. I'm not a person or a robot. I'm software here to help." So it tries to, really manage expectations. However, when you look into the actual behavior, they generate very human-like output. So what we did here, we basically took prompts from a corpus called Persona Chat. So this is a corpus which is all about your preferences, your hobbies, what you like to eat. And we took the prompts and we, again, piped them through all these systems and recorded the outputs. And then we annotated it according to a humanness score. So that's a score, an annotation scheme developed by Colledal called Living Machines. And you basically look for things like human emotions. So whether it says it likes something, or it loves something, or it hates something, and typical human activities such as sleeping, eating, and so forth. And what we found is that Google was actually the most anthropomorphized system, and Siri was the least anthropomorphized systems. However, we also observed an inverse relationship with not giving an answer. So especially Siri had a very high percentage of not being able to answer these questions, simply not understanding what the user was asking in this case. So to briefly summarize, I've argued that responsible conversational AI needs to work as expected. And here I briefly talked about hallucinations and how to mitigate these hallucinations. Then I moved on to open domain systems, and I argued open domain systems need to be safe. I briefly talked about the three-way classification of different safety issues, and then the safety kit, which you can use to evaluate your system. And I briefly talked about possible mitigation strategies, including knowledge grounding for open domain systems. And then finally, I talked about bias, and here I mainly concentrated on how the system design actually really matters and how it influences user behavior. Finally, I also want to add that all of these are obviously human values, and human values are typically subjective, they are varied, and they're multi-perspective. So that's what I briefly mentioned when I criticized the current approaches on supervised classification. They don't really take this into account. And sort of as a response to that, we organize a workshop at LREC, which we call NLP Perspectives, which is all about perspectivist approaches to disagreement in NLP. So the idea is that typically you would dismiss annotated disagreement as noise, but in some cases, and especially for subjective tasks such as toxicity classification or safety, there's an argument to be made that this is not necessarily noise, but also just different opinions, which is actually important and valuable to represent in the data and also represent in the models. So if you, so registration for LREC, early bird registration for LREC closes tomorrow. If you register, please consider taking part in our workshop. Finally, I briefly want to mention some work I didn't talk about, which is also very important, which is safety and robustness. And here I work with the RNIB, so that's the Royal Institute for Supporting Blind and Partially Sighted People, and our company Alana. We're trying to build robust models for visual question answering and for visual dialogue. So for example, in this example here, the person holds a bottle of drugs, of medicine, and the system is telling the user that you're holding a bottle of seasoning, which you can obviously see that in the context of vulnerable people, such as the blind and partially sighted, this could lead to quite severe safety implications. If you pour that over your dinner, in the best case, your dinner tastes a bit weird. So that's also something which is part of, responsible design. Last but not least, if you enjoyed this talk, we're hiring at Alana. I'm also looking for a postdoc in generating counter speech, which is starting later this year. So if you're working on generation and especially open domain generation, and you're interested coming to Edinburgh, please get in touch with me. So I think that's the end of my talk. Thank you for bearing with me, and thanks for listening.
Well, thank you very much for your very